Okay, so we'll now start a new chapter, chapter 2, the Lebesgue measure. So this is the most important measure which we will study in this course, and therefore we will do it in a little detail. Okay, so we remember the Cartesian thing. So you start with a non-empty set, and then you have a ring and a measure on it. Then you go to the hereditary sigma ring, which has a natural outer measure, and then you have the set of all mu star measurable sets, and you define a measure on it which is the same as mu star, and then of course you show that in fact this contains both R and S of R, and therefore mu bar is an extension. So this S bar with mu bar, that gives you a complete measure, and this is the process which you are going to apply. So we are going to start with R. So we will do everything in R, but this, you will see immediately how to extend it to Rn. So in one go we will finish everything. So if you take R, recall that we had this example, P is equal to set of all AB, A less than or equal to B, semi-closed, semi-open intervals. Okay, so if A equal to B, then you say AB is the empty set. This is the definition, convention which we are doing, and we are going to define on this mu of AB equals B minus A. And then if you take R, which is the ring, so all finite unions from P, and you can also, we saw that this is all finite disjoint unions from P. So if you take AE to be a set which is union Ij, J equals 1 to N, where Ij belongs to P, and then Ij, J equals 1 to N disjoint, mutually disjoint. Okay, so then it is almost obvious, because you have a measure has to be additive, in particular countably additive, and in particular additive. Therefore mu of E, we are more or less forced only for this definition, sigma J equals 1 to N mu of Ij. But then any set E, which is a finite union, you may be able to write in more than one way as a finite union of disjoint intervals like this, and therefore we have to show that this is well defined. And then we must of course show, is this countably additive. If we do these two things, then mu will be a measure on a ring, and then Cartesian's method will take over, and whatever complete measure we get there, that will be called the Lebesgue measure. So series of technical results which we need to prove, they are all more or less obvious, so we will have to write them down carefully, especially the first few results. So lemma 1, okay, A, let EI I equal to 1 to N be a finite set of mutually disjoint intervals in P. Such that each is contained in E0, which also belongs to P. So you have a disjoint set contained in P, then here is the first obvious result, I equals 1 to N, mu of EI is less than or equal to mu of E0. It's more or less obvious, you don't have to, we will anyway write down a formal proof, but yes, let F equal to A0 B0, be a finite interval, closed interval, contained in the finite union of open intervals ij equals aj bj 1 less than equal to j less than equal to n. Then again obvious or more or less obvious, b naught minus a naught, the length of that interval is less than equal to sum of all these intervals, so sigma j equals 1 to n bj minus aj. Okay, proof. A. So you write ei equals ai bi 0 less than equal to I less than equal to n. Okay, so now since ei's are disjoint, we can assume without loss of generality. So you can renumber them in a suitable way so that it's contained in a naught b naught. So a naught will be less than or equal to a1 strictly less than b1, less than or equal to a2 less than b2, etc. less than or equal to bi minus 1 less than or equal to ai. So this will be less than or equal to ai less than bi, ai minus 1 less than bi less than ai less than bi less than or equal to ai plus 1 and so on, less than or equal to bn which is less than or equal to b naught. Okay, so thus this implies that sigma mu of ei I equals 1 to n is nothing but sigma I equals 1 to n bi minus ai, and then you add all the missing portions. So this is less than or equal to sigma I equals 1 to n bi minus ai plus sigma I equals 1 to n minus 1 ai plus 1 minus bi. And then this telescopic sum becomes b naught, bn minus a1, and that is less than or equal to b naught minus a naught, which is mu of e naught. Okay, so that proves A. Now what about B? So again renumber if necessary the ui and get rid of superfluous ones so that you have bi belongs to ai plus 1 bi plus 1, which is equal to ui plus 1. Okay, so the intervals are like this: is the first one, then the second one, then the third one, and so on, and the fourth, so on. So you each time the intervals are is contained in the next one. Okay, so that's how we are going to write them. Okay, so we number them like that: 1 less than equal to I less than equal to m minus 1. If there are some more, so m is less than equal to n. So we have got rid of some extra ones which may be the repetitions of these sets and so on. That only adds to the right hand side of this equation here, and therefore getting rid of any sets, proving it for smaller number is not a problem. That still does proves the same thing. Okay, so and also A naught must belong to the first interval u1, and B naught must belong to um, the last one. Okay, so you are taking only the minimum number necessary to cover A naught, B naught. So again, B naught minus A naught is less than Bm minus A1, which is equal to B1 minus A1 plus sigma I equals 1 to m minus 1 Bi plus 1 minus Bi. So I am writing as a telescopic sum, and that is less than or equal to sigma I equals 1 to m of Bi minus Am. Because you have that Bi is contained in Ai plus 1. Okay, so that is why you have you get this, and therefore that proves this theorem. Okay, so this is the first technical lemma, which is really nothing. Just intuitively, if you drew pictures, the proof will be obvious. Okay, so now proposition, let me call it 1. If Ei I equal to 0 to infinity is a sequence in P such that E naught is contained in union Ei I equals 1 to infinity, then mu of E naught is less than equal to sigma I equals 1 to infinity mu of A. Again, this is almost obvious, so we will proof. Trivially true if E naught is empty. There is nothing. So let us take Ei equals Ai Bi, 0 less than equal to I less than infinity, and then Ai strictly less than Bi. So all the intervals are disjoint, and you choose epsilon positive such that 0 is less than epsilon less than B naught minus A naught, because B naught minus A naught is A naught B naught is now a non-trivial interval, and therefore B naught minus A naught is strictly positive by this condition here, and therefore you can choose an epsilon like this, and then let delta be an arbitrarily small positive quantity. Okay, so then you set F naught to be A naught B naught minus epsilon. So this is of course contained in E naught, and you define Ui equals Ai minus delta by 2 power I Bi, and this of course contains Ei. And therefore F naught is contained in union I equals 1 to infinity Ui, and F naught is compact because it's a finite closed interval. It's compact, implies there exists a finite subcover. So let us assume that F naught is contained in union I equals 1 to m Ui. So you have a closed interval and open intervals, finite number, and therefore by lemma part B, of course, you get that the length of F naught, which is B naught minus A naught minus epsilon, is less than sigma I equals 1 to infinity of sigma I equals 1 to n, bi minus ai plus delta by 2 power I, which is less than or equal to sigma I equals 1 to n infinity bi minus ai, which we will keep, and then this sigma delta by 2 power I is a geometric series which adds up to delta. So in other words, that is mu of E naught minus epsilon is less than or equal to sigma mu of Ei plus delta. So you let epsilon delta go to 0 and you get the proposition. So proposition 2. So mu is countably additive in P. We are saying mu is countably additive in P, not we want actually in R, but this is going to be the first step. So proof. So E naught equals union I equals 1 to infinity Ei, E naught, Ei are all in P, and then Ei, I equals 1 to infinity mutually disjoint. So by proposition 1, we have mu of E naught is less than or equal to sigma mu of Ei, I equals 1 to infinity. By lemma A, for every n, we have sigma I equals 1 to n mu of Ei is less than or equal to mu of E naught, and that since is true for all n, so this implies mu of Ei is less than or equal to mu of E naught. So mu of E naught is less than or greater than the same quantity, and therefore the two are equal, and therefore you have that mu of E naught is equal to sigma mu of Ei. Okay, so that proves that it's countably additive in P. Okay, so now we have a theorem. There exists a unique finite measure mu on R which extends mu on P. Okay, so we have found a ring. Okay, so proof. So let E belong to R. So E is equal to sigma union Ei, I equals 1 to n, Ei in P, Ei disjoint. So we are more or less forced to define. So mu E equals definition. We cannot I equals 1 to n mu of Ei. Only we have to check that this is well defined because it may have a different decomposition. So we assume, so well defined. So we take E equals union Ei, I equals 1 to n, equals union Fj, j equals 1 to m, Ei disjoint, Fj disjoint, Ei Fj are all in P. Okay, so this is what we have. Okay, so then we have E. So for all 1 less than or equal to I less than or equal to n, we have Ei is nothing but the union j equals 1 to infinity Ei intersection Fj, and then for all 1 less than equal to j less than equal to m, we have j equals 1 to m. So this is clearly finitely additive. Okay, because you put together finite number of disjoint finite unions, so sum will just add up, and therefore this is clearly finitely additive. Now ei equals ei intersection fj, and for all j 1 less than 1, you have fj equals union I equals 1 to n fj intersection ei. Okay, so mu of E. Now intersection of two elements of P is either empty or it is an element of P, and EI is the union in this. So we saw in the proposition 2 that it is countably additive in P, therefore it's also finitely additive in P. So mu of EI is nothing but sigma j equals 1 to m mu of EI intersection fj. So this is proposition 2 and finite additivity. Since EI intersection fj belongs to P and EI is anyway in P. Okay, and therefore sigma mu of EI. Okay, similarly mu of fj equals sigma I equals 1 to n mu of EI intersection fj. Okay, so sigma I equals 1 to n mu of EI equals sigma I equals 1 to n sigma j equals 1 to m mu of EI intersection fj. This is a finite sum with, and therefore I can write j equals 1 to m sigma I equals 1 to n mu of EI intersection fj, and this is equal to sigma j equals 1 to m mu of fj. And therefore whether you define it as sigma mu of EI or sigma mu of fj, it doesn't matter, the answer is it's the same. So mu is well defined and clearly finitely additive, because you put together. So let me not say that here, so we will say it here. Now that it is well defined, I can say it with greater confidence. Okay, so now to show mu is countably additive, that's all we need to show. So we take E in R and E equals union I equals 1 to infinity EI, EI in R and EI I equals 1 to infinity disjoint. Okay. So each EI belongs to R, so EI equals union K equals 1 to Ni EIK in P. And mu of EI is equal to sigma K equals 1 to Ni of mu of EIK by definition. Okay, so now case 1, E itself belongs to P, so E is in R. Okay, so E may belong to P itself. Then of course E equals union I equals 1 to infinity, union k equals 1 to ni eik, and this is disjoint union in P, and therefore by proposition 2 we have that mu of E equals sigma I equals 1 to infinity, sigma k equals 1 to ni mu of eik, because you have countable additivity in P, and that's equal to sigma I equals 1 to infinity mu of ei, and we are through. Case 2, okay, so E equals union j equals 1 to n fj in P, and fj j equals 1 to n mutually disjoint. Then fj equals union I equals 1 to infinity of fj intersection ei. So this of course belongs to R, each of these belongs to R, and this belongs to P. So by case 1 you have mu of fj equals sigma I equals 1 to infinity mu of fj intersection ei. So mu of E, and this is by definition sigma j equals 1 to n mu of fj equals sigma j equals 1 to n sigma I equals 1 to infinity mu of fj intersection ei. And now this is finite sum, this is infinite sum, everything is non-negative, no problems. So sigma I equals 1 to infinity, sigma j equals 1 to n mu of fj intersection ei. Ei intersection fj, j equals 1 to n, is finite disjoint collection in R, and so by finite additivity of mu in R, okay, we have already said clearly finitely additive. Okay, so by finite additivity in R you have that, and you also have ei equals union j equals 1 to infinity ei intersection fj, and therefore you have that mu of ei equal to sigma j equals 1 to n mu of ei intersection fj, and that is exactly this quantity here, and therefore you have mu of E equals sigma I equals 1 to infinity mu of ei. Okay, so this proves completely that we have a measure on this. So remark, in Rn define P equals set of all product I equals 1 to n of ai bi. So these are rectangular boxes, each is one on, if you take a pair of opposite sides, one side is closed, other side is open, ai less than or equal to b. And then you define mu of pi I equals 1 to n ai bi, equals product I equals 1 to n of bi minus ai. Okay, and then you define R equals finite unions from P equals finite disjoint unions from P. Then exactly as in the case, only your notations, computations will be a little messy, but there is no ideological, no difference from the arguments or the ideas involved. So exactly as in the case n equals 1, there exists a unique measure mu on R. Okay, so this namely the sum of all the, which is if E equals union EI, I equals 1 to n, 1 to small n, EI in P and EI disjoint, then you have mu of E equals sigma I equals 1 to n mu of EI. Okay, so this is exactly the definition in Rn. So what we did in R1, we can also do in Rn. Okay, so now we have a ring, we have a measure, and we are ready to apply Carathéodory's method to construct the Lebesgue measure. And as I said, what we have done in case n equals 1, also we can do similarly in any general dimension, and therefore we will to construct the Lebesgue measure in all dimensions next time. Okay.